Hello everyone. Let's start today's Hello everyone. Let's start today's lecture. In the past 2 weeks we have talked about the what are nanomaterials, what is the significance of the nanomaterials, and then in the second module we saw the applications as well as the quantum confinement in the nanomaterials. In today's lecture we will talk about the synthesis of nanomaterials. How can we how can we synthesize nanomaterials? So in this week there were four lectures. One was about the various techniques which are required for the synthesis of the nanomaterials, and the second is the next lecture is about how can we control kinetically and thermodynamically. So there are various theorems about that. That one is nucleation theory, and learn about the critical radius, undercooling, and all these things. And then the most important part of today's lecture is how the explanation of the different techniques. There are two techniques. One is the top down, and the other one is bottom up. So these two are important techniques, and this has a various parts which we are using in our for the fabrication of the nanostructures. Based upon the feature size, we decide the technique. Based upon the utility of the nanomaterials and the application, we choose uh, a specific technique which is used for the synthesis of the nanomaterials. So, the synthesis of nanomaterials is fundamentally the process of producing materials with dimensions in the nanoscale range. What was that range? We saw in the first lecture that one of the dimension should be lesser than the 1 to 100 nanometer. It should lie in this range. Then only we will say the nanomaterial. So we want to produce materials with dimensions in the nanoscale range. Apart from that, what we want to control? We want to control the size, shape, kim- so we want to, there are various things like shape, size, then composition, and also surface properties. So the important point is that synthesis at the nanoscale is not simply about making a material smaller. The challenge is to control the formation and growth of nanostructures. So there are two fundamental approaches. So one is top down and the other one is bottom up. So what will happen in the top down approach? In the top down approach, so like this is we saw that like why synthesis matters. So synthesis is the controlled production of materials with at least one dimension between 1 to 100 nanometer while controlling the size, shape, composition, and structure. Then, so what will happen if we are controlling the size, the strength, reactivity, and optical absorption, and band gap and electrical conductivity. This we have already seen in the first two lectures. It will all change sharply as the particle size will approach to nanoscale. Then, like it also fixes purity, dispersion stability, biocompatibility, and then what is the process norms like temperature, pH, reaction time. So These are the things which we are using to tailor final nanomaterial properties. Now, so when we are talking about the top-down approach, what it is doing in the top-down approach, we start with the bulk material and we are continuously reducing its dimensions until the nanoscale structures are obtained. So what we have, first we have bulk material, then we are doing in we are doing the fragments, and like first microstructure and then nanostructure. So it is similar to taking a large block of material and carving or breaking it down into smaller structure. So there are various techniques for the. So how can we break bulk material down to nanoscale? So we can use the physical methods, chemical methods, and mechanical methods, and there are some hybrid methods also, which includes a chemical process as well as physical process. So using these processes, it can. So when we are following this approach, it can introduce the surface roughness defects, but with the control. So, and what is the bottom up? In the bottom up approach, first we will have the atoms and molecules, and then it will assemble and it will make a cluster, and then it will convert into a desirable size or nanostructure. So, so what is this? Assembling matter from atomic and molecular precursors. So it is cost effective with minimal material waste and precise control over surface chemistry. But on a large scale, it is not preferable. So now, so as we saw that there are various approaches like physical approach, chemical approach, biological approach, and hybrid. So in case of physical approach of the synthesis of the nanomaterials, uh, there are various techniques. Uh, Among them, one is mechanical milling. So mechanical milling is also known as ball milling. So here what is happening in the ball milling, so bulk material is placed in this chamber. So some of the important properties that we have to take care of, like this jar should be made up of a harder material. So if we are milling that, it should not there should not be any harm. There should not, the components whatever we are nanostructure or bulk material placing, it should not react with the material of the jar. Otherwise what will happen, the nanostructure we are creating, it will, if it is reacting with the walls of the jar or chamber, the impurities will come and it will change the desired properties of your nanostructure. So here what is happening, bulk material we will place in the steel or aluminium jar with the hard milling balls, and then the chamber is rotated. So what will happen, by repeating fracturing eventually reduces the particle size to the nanoscale. But for this process, this milling process, what it can give you, so milling, it can cause the defects, it can cause contamination and strain also, and non-uniform particle size distribution. So these are the things that generally happens when we are reducing the size. Now, like what can we do or how can we improve this? So first of all, by ensuring the material of the chamber suitable for the ball milling, we can reduce the contamination. Second thing is, if there is a non-uniform particle size, what we can do, we can uh, we can do so the milling is done in a liquid environment. So we keep some slurry which is not reacting with the our nanostructure element and the jar element, such that there can be some uniform distribution of the particle size. So although like this is a simple and scalable, it doesn't always provide like excellent control over the nanoparticle size and morphology. So this was one physical technique which we are using for creating the nanoparticle sizes. The next is melt mixing. So in this technique, it's also a physical method which we are like mainly this technique is mainly using for preparing the polymer composites. So this is so unlike chemical synthesis methods such as like sol gel method, we will talk about that. Here we generally don't synthesize the nanoparticle themselves. Instead, pre-existing nanoparticles are dispersed into a molten polymer matrix. So what is the basic idea behind this? So we have a polymer, then we will take the nanomaterial precursor. So it is nanofiller. Then we will heat plus shear, and then it will give you a polymer nanocomposite. So how does it work? So first of all, the polymer is heated. Obviously, if we want to add some material, we have it should be uniformly distributed inside that. So what we are doing for that, we are taking the polymer. We are heating it above its melting temperature so that it becomes viscous and can flow. So then after that, in molten polymer, nanoparticles or nanofillers are then introduced into this molten polymer, and then the mixture is subjected to mechanical shear uh, uh, by using the equipment such as internal mixer or some like there are some other mixers come, thin screw extruder. There are some uh, equipments for the mixing. So what will happen then, this force will help break up nanoparticle. So we should prevent the agglomeration. So if the force will continuously break up the nanoparticle, so it will prevent it from agglomeration and distribute the nanofiller throughout the polymer. Then finally the mixture is then cooled and it will become a solid nanocomposite. So like why is that shear force important? So because nanoparticles have a strong tendency to form a aggregate because of their high surface energy that we have already seen in the previous lectures in the surface to volume ratio and regarding its Gibbs free energy and the surface energy. So if we will simply mix the nanoparticles with polymer, it is not sufficient. So during melt mixing, mechanical shear acts on the agglomerates and it will if there is some agglomeration, then it will prevent that. So quality of our final this polymer nanocomposite will depend on the uh, mixing temperature and mixing time, shear rate, also like viscosity of the polymer, and what is the interaction between uh, nanoparticle and polymer. So this is for the what are the so what are the advantages of this process, that is a solvent free process. In ball milling we need some solvent in which the milling is happening. It needed some environment for that process. It is simple and relatively economical and solvent free process, and it's easily scalable also for industrial production, and there is no need to synthesize the nanoparticles during the mixing process. So but what are the limitation of that? So the major challenge is uniform dispersion. So since nanoparticles tends to agglomerate, and excessive shear or temperature can sometimes damage also the nanofiller or degrade the polymer. uh, so that's why, like, so with the although it is scalable, but still there is a non-uniform dispersion. So this is one technique of top-down method in the physical synthesis of nanomaterials. Now the next is PVD. So in PVD, this is what is the full form of PVD? PVD itself is saying that physical vapor deposition. So it is a top-down physical deposition technique. Which why it is useful? Using this technique, we can produce thin film coatings and nanostructured materials. So, unlike melt mixing, where we were dispersing nanoparticles into a polymer, PVD forms the deposited material by converting a solid source. So, in this technique, what we will have a solid source. We'll have a solid source. Then we will convert it into vapors. Solid source will convert into vapors, and then we will that vapors will deposit on some substrate. So we will have some substrate. So from this solid source, some thin layers will deposit onto this substrate. So what is the basic principle is, we will have solid source, then vapors, then it will transport and it will condensate on this substrate. Then we will have a thin film nanostructure. Thin film or nanostructure. So what is the principle of this? Suppose we want to deposit a uh, titanium thin films. Okay. So now we should have a titanium in the bulk form. So we will take the target of titanium. Now this solid material will like first converted into atoms or molecules in the vapor phase. And how is it done for PVD? So this is usually done under high vacuum, so that so all these techniques where the thin films we deposit like PVD, CVD, and sputter, all these uh, techniques require a high vacuum. Why high vacuum is needed? So this technique needed high vacuum. So why high vacuum? So that the vapor particles can travel towards the substrate without undergoing too many collisions. And with the gas molecules. So when these particles will reach the substrate, they will lose energy and condense on its surface. So eventually a thin film will form. So why is vacuum required? So we because we want the evaporated atoms or particles to travel from the source to the substrate. Suppose we don't have the high vacuum and we are operating a PVD at the atmospheric pressure, then what will happen? While traveling, they will frequently collide with the gas molecules. So they will lose their energy in between the path and they won't reach to the substrate and deposit. So under vacuum, fewer collisions will happen and longer mean free path. So therefore the vapor particles can travel more directly and travel towards the substrate. So lambda is, so we can say that the mean free path is related to, so reducing the pressure will increase the distance a particle can travel before the colliding. So what are the, so we have seen the main steps: vaporization, transport, deposition. Now, okay, so there is one important thing. When I'm saying that the first part is vaporization, then how are we vaporizing the material? So there are two major PVD techniques. First is thermal evaporation. In the thermal evaporation, the source material is heated until the molecules, atoms or molecules evaporate. The heating can be achieved using resistive heating or electron beam heating. So there is also one instrument called e-beam evaporator, in which, so one is thermal evaporator. In thermal evaporator, we are heating it through the resistive heating, and the other one is electron beam, where the electrons are striking and then the material electron is striking to the target, so that's why it is getting melting. So for materials with high melting point, we prefer the e-beam evaporator, so preferable for high melting point materials, uh, because a focus electron beam can provide very high localized heating. So this is one technique. The other technique is sputter. So here in the sputter, we don't simply heat the source. Here what we are using in the sputtering process, we are using the energetic ions are used to physically eject atoms from a solid target. So what is happening here? Okay, here also I have mentioned that, like in uh, okay, we were on sputter. So we are dealing with the energetic ions. Okay, so in this system, what do we have? A target, a substrate. It is also done at the low pressure and high vacuum. So target, substrate, and one inert gas. In sputter process, we use argon. So since argon will not, we use inert gases because they don't react with the other atoms. So why are we using the argon atoms to generate a plasma? So what we will do, first argon gas is introduced at low pressure, and to create the ions, we are applying the voltage which will generate ions. So the positively charged argon ions will are accelerated towards the negatively biased target. So they will strike the target with sufficient energy. Then what will happen? Argon ion plus, if they are hitting that target, so argon atom plus target atom. So ejected atoms will travel towards the substrate and form a film. So what we did first, we created a plasma using argon ions, and then ion bombardment, and then target atoms ejected, and then the thin films are formed. So it is totally different from the PVD, where we are using the thermal evaporation, where we were using the heat for the film growth. But in this case, we are using the plasma. So since, why are we saying these are the physical techniques? Because the target atoms are physically removed rather than the chemically produced. So uh, the final film, the morphology of the final film depends upon the substrate temperature, deposition rate, pressure, surface energy, substrate material, and the incoming particle energy. So, so this is the this sputtering technique. So next, okay, so let's like quickly look up this high energy ball milling. What was it? So mechanism was, the we have a powder plus hardened steel or tungsten carbide walls. Since we need a chamber such that it should not harm during milling, these both will rotate together in a container, and repeated collision and frequency will fracture particles and cold weld them, and it will refine, like it will convert into nanomaterials. So you can see what is the yield is this, the milligrams to kilogram within minutes to hours. And so using this we can create the nanocrystalline alloys and oxides. And what is the limitation? So broad particle size distribution and risk of contamination. And the next is melt mixing, in which we were dispersing the nanoparticles into molten polymers. Using shear force, we were generating the polymer nanocomposites, and these are compatible with the standard industrial extrusion lines. And so the cooling rate is, so we also saw that what are the thing that decides the outcome. So if we are doing the slow cooling, it, it can create the homogeneous or inhomogeneous nucleation, long range order crystalline solids, and fast coolings, controlled reheating. So why it matters? So glass derived nanocrystals combine the processability of glass with size tunable optical and magnetic properties, and we are using these techniques in glass ceramics and magnetic recording media. Then we have already completed this PVD process. The next was ablation in the physical technique process also. So what is laser ablation? This is also a top down physical process for producing the nanomaterials. What are we doing in this? In this, a high energy laser pulse is focused on a solid target. High energy laser pulse is focused onto a solid target, and so what will happen? So the intense laser energy will remove the material from the target and will converts it into a plume that will contain the atoms, ions, molecules, and clusters. So these species subsequently cool, nucleate, and form nanoparticles. So what is the process? The process is, we will have a solid target, high energy laser, then it will convert into plume, then nucleation, and then nanoparticles. So this is the process, and so like what we are doing, a pulse laser is focused onto the surface energy. So since it is a pulsed, the energy will be high for a very short duration. Then the target will absorb that laser radiation and it will produce a rapid heating. So if the laser fluence is sufficiently high, the material is removed from the surface. So and when it will, so the plume will initially has a very high temperature and energy. So when it, like as it expands, it cools. So during cooling, the atoms and clusters can interact and form large clusters. So it is, so the laser ablation is a top down physical method, but the actual nanoparticle formation involves nucleation and growth process after the material is removed from the uh, target. So this is one method. The next is laser pyrolysis. So what in this process, okay, so this is a bottom of actually. So here, okay, so the next is arc discharge. So we have seen about mechanical milling, melt mixing, PVD, sputter, laser ablation, and then this arc discharge is also, so it's a physical method, but it's a bottom up method. So bottom up technique that is using for synthesize the nanoparticles, and this method is used for generating the carbon nanotubes and also the graphene related structures like fullerenes. So what, like what is the basic idea for this arc discharge? So what is happening? So we are creating a very high temperature electric arc between two electrodes. So it's a high temperature electric arc between two electrodes. So what will happen? The intense, it will create the intense heat, and that will vaporizes the material from the anode. So and the vapor will subsequently cool and condenses to form nanostructure. So first we will have the solid electrode, then electric arc, it will produce the vapor, then cooling, then nucleation, plus nucleational growth, and the finally we'll get, will have the nanostructures. So, like, what is the basic principle? In this setup, we will have the two electrodes, anode and cathode. The electrodes are placed very close to each other inside a controlled atmosphere. So, we are using an inert gas like helium or argon. Then, a potential difference is applied between them. So, when the electrode are brought sufficiently close, the gas between them become ionized and it will and an electric arc will form. So then this arc will form, high temperature, even thousands of Kelvin, and then this intense heat will cause the anode material to evaporate, and this vapors will move away from the hot arc region and it will cool. So during cooling, then it will form a, so like using this we are forming the carbon nanotubes. What is happening, so our uh, the carbon vapors, depending upon the condition, the products can be from like amorphous carbon, carbon nanoparticles, fullerenes. So it depends strongly on the electrode composition and discharge condition. Suppose if we are using catalysts such as transition matters, if we are incorporated into the anode, then it will form the nanotube formation. So what are the catalysts we are using? Like iron, cobalt, and nickel. These catalysts help to facilitate the nucleation and growth of the nanotubes. And electric, like arc current, will control the nanomaterial formation. So this is a one bottom up technique, and it is a physical technique to create. So what is the advantages of this electric arc discharge method? So this can produce a highly crystalline carbon nanostructures. Why is it so? Because the synthesis is happening at a high temperature. It gives us high yield also compared with the other carbon nanotube synthesis methods. And what is the limitation of this? So it can produce a mixture of nanotubes, amorphous carbons, and nanoparticles. So purification is not there. So if we compare between electric arc discharge and laser ablation, uh, in both the processes, we need the higher temperature plasma, in which one is using the electric arc to generate that plasma, and the other case it is using laser. So the principle is common, like energy we are giving, vaporization is happening, cooling is happening, and then the nucleation and then nanomaterial. It's just that the production of, in one case it is there is optical energy, and in the other case it is electrical energy. So this was all about the electric arc discharge, in which we are forming the carbon nanotubes and the amorphous carbon fullerenes using this technique. So next is, so these were all the physical methods for the synthesis techniques for the nanomaterials. Next is chemical techniques. So for the chemical processes, now there is no direct heating on the target molecule, although it will there will be some reactions involved. So in the chemical processes, the first process is colloidal synthesis. So this is a bottom up technique. So in this technique we will use some chemical methods for producing the nanoparticles. So what is happening in this method? In this method, atoms and molecules will generate from the chemical precursors. So we will use some precursors in a liquid medium, and then it will undergo nucleation and grow to form nanoparticles that will remain dispersed in the liquid as a stable colloid. So what is the basic idea? Chemical precursors, then nucleation, growth, and then colloidal nanoparticles. So what is colloid? So in what so like before understanding the synthesis we need to understand the word colloid. The colloid is a system in which very small particles are dispersed throughout another phase. So for nanoparticle synthesis we have nanoparticle dispersed in a liquid. Suppose gold, for example, gold nanoparticles dispersed in water form a colloidal gold solution. So gold, colloidal gold solution. Gold nanoparticles dispersed in water. So the nanoparticles are small enough to remain suspended rather than immediately setting under gravity. So suppose we want to synthesize metal nanoparticles, so we have to have some metal salt that will contain the metal ions. So then we should have a reducing agent that will convert the metal ions to neutral atoms. So, as more atoms are generated, the concentration will increase, and eventually the solution will become sufficiently supersaturated such that the atoms will begin to cluster. So, the nuclei then grow. First, atom is forming. First, atom is forming. Then there is nucleation, and then nanoparticles. So, like for the colloidal synthesis method, three important components. One is precursor. Mm, Second is reducing agent, which will convert metal ions into neutral atoms. And the third is agent. So, what will capping stabilizing agent or capping agent? What it will do? It will prevent the formed nanoparticles from aggregating. So, because the tendency of nanoparticles is to aggregate. So, if we are using some capping agent, it will stop that. Then, after this process, then the nucleation and growth will start. So, the what stage one first is nucleation will happen. In the nucleation, the precursor will be converted into atoms or monomers. When the concentration will reach a critical value, the nucleation will begin. So monomers will convert into stable nuclei. Then what is stage 2? Then the growth will start. So after nucleation happens, the additional atoms will start attached to the existing nuclei, and then so therefore what is the difference between nucleation and growth? So nucleation determines the number of particles, while growth determines how large those particles become. So this is the way of the synthesis of nanoparticles using the colloidal solution. Then comes how can we control the particle size. So since we know that a reaction produces many nuclei, so the available material has to be distributed among many particles. So the outcome will depend upon the reaction kinetics and the growth mechanism. The temperature also uh, plays an important role in colloidal synthesis. So if we increase the temperature, it can affect the reduction rate, diffusion, and nucleation, growth. So and depending upon these reaction condition, we can obtain the nanospheres. So, like, what will be the shape of the nanoparticles? So, the environment in which we are synthesizing the nanoparticles, depending upon the reaction conditions, nanospheres, nanorods, nanocubes, nanocrystal. Why is this happening? Because like different crystal facets will grow at different rates. So if the growth along one direction is suppressed, then the particle may develop an anisotropic shape. So that's why the reaction conditions plays an important role in the colloidal synthesis, and the size and shape of nanoparticles are primarily controlled by controlling the rates of precursor conversion, nucleation, growth, and surface stabilization. So this is the process of the synthesis of nanoparticles using colloidal synthesis. The next is sol gel process. So what is sol gel process? It is also a bottom up wet chemical method for synthesize nanomaterials. This method we are specifically, just like arc discharge we were using for making carbon nanotubes. Similarly, soldier process we are using particularly for molecular metal oxides and oxide-based nanocomposites. So it is based on a converting a molecular precursor into a colloidal suspension. So what is sol and what is gel here? So when we are converting a molecular precursor into a colloidal suspension, we are saying it's sol, and then into converting into three-dimensional solid network, it is called gel. So what is the basic sequences? So the sequence of this, we have precursor, then hydrolysis, then condensation. So now the this is colloidal solution, then sol it is formed, then it will create the 3D network, then it will get dry, and then the formation of nanomaterial. So the name comes from the two important states formed during the process. Sol is a colloidal suspension containing very small solid particles or clusters dispersed in a liquid. And the gel is formed when these particles or more species will become interconnected, and it will produce a three-dimensional network that will trap the liquid within it. So the starting material, so there are two common types are metal alkoxide, uh, mm, metal alkoxides and metal salts. So in metal alkoxides it comes MORN. So M is a metal and OR is an alkoxy group. So the common precursor, like there is one example like SiOC2 H5. So this precursor is mixed with a suitable solvent that will create an alcohol along with water. So step one is we will do the hydrolysis process. So MOR will react with water. Water will react with metal oxide. It will give MOH less alcohol. It will give us hydroxyl group. Then so then the extent of hydrolysis will depend upon water to precursor ratio, pH level, temperature, solvent and catalyst. The second step is condensation. So after hydrolysis, the hydroxyl containing part will condensate. So MOH will give us MOM plus H2O. So the important product is this one. This MOM, and it will create, so repeated condensation, what it will do, it will create a long chain. So hydrolysis and condensation proceed, then like this a 3D network will create, and tiny particles or polymeric clusters will begin to form, and these will remain dispersed in the liquid, so that's it is called the sol. As the condensation will continue, the clusters will begin to connect with one another, and eventually a three-dimensional network will develop throughout the liquid, and this liquid will trap inside this network, and it is called gel. So it also with aging, further condensation occurs, the network becomes stronger, structure rearrangement can also occur, some liquid may redistribute. So the aging condition can affect the final pore structure and mechanical properties. Then the gel contains a large amount of liquid. So drying method will strongly affects the final structure, and then like we can after drying also material can contain some organic groups or solvents. Therefore, we give some heat treatment that is called calcination. So the temperature must be carefully controlled, because excessive heating can also cause small nanoparticles, and it is by heating it is converting into larger grains. So calcination can improve the crystallinity, but also it may also increase the particle size also. So this is the process that this is one of the important process for the synthesis of nano materials using the chemical process, and this is a bottom up technique. So what are the limitation of this, when we were drying this nanomaterials, there can it can cause cracking, long processing time. Since it is trapped in the liquid, there can be some residual of organic group, so it can give the impurities, so the purity is lesser. So if we compare between colloidal synthesis and sol gel, so in colloidal synthesis we were dispersing the nanoparticles in the liquid, and in the sol gel process it is producing a molecular and colloidal network that evolves into a gel. So it colloidal synthesis mainly for the metal nanoparticles, and sol gel process for the metal oxides. uh, so this was the sol gel process. Now coming to the next process, which is the hydrothermal. So the hydrothermal synthesis, it is also a bottom up chemical method in which which is used to synthesize highly crystalline nanomaterials, particularly sulfides, hydroxides, phosphates, and other organic nanostructure. So what is the basic idea of like what it will happen? Hydrothermal. Hydro means water and thermal means temperature. So the word itself is saying that the reaction will take place in water at elevated temperature and pressure inside a sealed vessel. So what will happen in this process? We will have some precursors plus water. Then what will happen? We will give the high temperature and high pressure. Then nucleation and growth will start, and then the nanomaterial will get the nanomaterial. So why do we need high pressure? So if we will heat the water in an open container, if we will reach the boiling point, water will start converting into vapor, and the temperature cannot increase much at atmospheric pressure. So but in hydrothermal synthesis, the reaction we are carrying out in a sealed autoclave. So as the temperature will increase, water vapor pressure will increase. Since the vessel is sealed, the pressure will increase. So therefore, water can remain in a liquid at temperatures significantly above its normal boiling point. So this will allow the chemical reaction and crystallization to occur under conditions that is not possible in an open vessel. So, like what is in our autoclave, we have a strong outer vessel, that is the chamber we are saying, strong outer vessel, and one an internal chemically resistant liner, then precursor solution and control heating. So if we are creating a metal oxide nanoparticle, first we have to dissolve suitable precursor in water, like metal salt plus water. So as the temperature will increase, the precursor species will become more reactive and the solution will become super saturated with respect to the desired phase. After that, the nucleation will start, and growth will start, and we will get the nanomaterial. So how can we control the nanoparticle size? So the final nanoparticle size will depend upon the balance between nucleation and growth. So if the nucleation is rapid, so nuclei will be rapid nucleation. Rapid nucleation, what will give you many nuclei, small crystals. If nucleation is slower and growth dominates, then what will happen? Smaller nuclei but larger crystal. So parameters like temperature, pressure, reaction time, what is the precursor concentration, all these things we can use to control the particle size. And we can control the shape by controlling the growth. If the growth is faster in one direction, it will create the anisotropic. So based upon that, uh, we can control the morphology of the nanoparticles, like nanorods, nanowires, nanosheets. We can create all these things. So we have covered up to hydrothermal. Um, we will continue after 10 minutes. Let's resume the class. So we have covered up to hydrothermal. Next is CVD. CVD, just like when we did PVD, PVD was physical vapor deposition. Similarly, the CVD is chemical vapor deposition. So the in case of CVD, it is also a bottom-up technique. Bottom-up technique which we are using for producing the thin films, nanowires, nanotubes. Also, the one important thing is 2D materials. So the fundamental idea is different from PVD here. So in PVD, what we were doing this, a material was physically vaporized from a source. In CVD, gaseous chemical precursors are introduced in a reaction chamber where the materials will precursors will react chemically or decompose at a heated substrate to form the desired material. So here the process is in CVD we will have the gaseous precursors, then transport, then there will be some reaction, then nucleation and thin film. So what is the basic principles? So this method we are also like nowadays we are producing TMDs. TMDs are transition TMDs or TMDCs we say transition matter dichalcogenides. So like MOS2, WS2, WSC2, MOSC2. So to generate this we are in using CVD. What we are doing, we are taking the precursors like MOO3 plus plus sulfur, then it will give us MOS2. Similarly, if we want WS2 WO3 plus sulfur, then it is giving. Suppose we want to deposit the silicon. So what will be the precursors? We will use the precursor SiH4. After at the hot substrate, it will decompose Si plus 2H2. So what are the main components of a CVD system? Precursor gas, carrier gas, gas flow controller. So for the formation of the thin films using CVD, we control like whether we are working in a argon environment or nitrogen environment or like how much SCCM of the oxygen is needed, what are the ramp time, what are the stabilizing time. So this is all the things happen, and using this only the size shape of the thin films is decided. So first step is transport, where the gaseous precursor will be transported towards the substrate. Then there is a gas phase reaction. So the precursor will undergo reactions and it will decompose before reaching the substrate. Then adsorption will happen. Then the desired material will begin to form nuclei and it will grow. So like we can grow the graphene using CVD and other two-dimensional materials. Uh, so also we can CVD is widely used for synthesizing carbon nanotubes also, and such as methane, ethylene, and acetylene. And sometimes we also use a catalyst for enhancing the growth rate. What are the important CVD parameters? Temperature, pressure, and gas flow rate. So also in CVD types also we have thermal CVD. So where the thermal energy will be used to activate the chemical reaction. We have the plasma enhanced CVD, that is PECVD. So where the plasma will be used to activate the precursor. The other one is one more metal organic CVD, that is MOCVD, where metal organic compounds are used as a precursor. Like um, so MOCVD is important for the semiconductor materials such as this gallium nitride, gallium arsenide, indium phosphide, like 3 5 semiconductors. So using CVD we can generate the high quality films. We can have the composition control, large area deposition, and we can deposit a large range of materials using CVD like oxides, metals, semiconductors, 2D materials. So, and but what are the limitations? Since it requires high temperature, so sometimes there can be toxic or hazardous precursors also. So these are the like CVD is a chemical method also, and it is like it is comes in under the hybrid process also, because okay. So the next is mini emulsion method. So in this method what we are doing, it is also a bottom up colloidal method which we are using to prepare the nanoparticles by creating a very large number of uh, stable droplets of one liquid dispersed in another immiscible liquid. So these droplets will act as a tiny nanoreactors inside which the nanoparticle will form. So what is the idea behind this? For this, the idea is we have the reactants, mini emulsion droplets, then nanoreactors, then reaction, and then the formation of nanoparticles. So, what is an emulsion? First of all, the emulsion is a mixture of two liquids that do not mix with each other. Suppose, for example, oil and water. So, these are naturally separate because they are immiscible. But if we apply sufficient mixing and add a surfactant, one liquid can be broken into tiny droplets and dispersed throughout the other. So, suppose oil droplets in water, it forms an oil in water emulsion. The important point is that the droplets will provide the small confined volumes in which the chemical reactions can occur. So, what makes it a mini emulsion? So, in a conventional emulsion, the droplets can be relatively large and may not be particularly stable. But in case of mini emulsion, we deliberately produce much smaller droplets, typically in the tens to hundreds of nanometer range. So, what will these droplets do? These droplets are stabilized against the collisions, aggregation, and Ostwald Rigning. We will study about this term later. Even this is one of the question in the assessment assignment also. So so these droplets effectively behave as individual nanoreactors. So this is the key concept. So basic components are Like mini emulsion system contains continuous phase, that is water, dispersed phase, an immiscible liquid containing the material that will form the nanoparticles. Then third is surfactant that will stabilize the droplets. Fourth is co-stabilizer. Sometimes it is added to improve the droplet stability. And the fifth is energy input. So high shear mixing or ultrasonication is used to break the dispersed phase into very small droplets. So after ultrasonication, large droplets will break into smaller droplets and it will act as a nanoreactors. So then, uh, then we can see that there will be a formation of nanoparticles. So if the droplets will be small, small nanoreactors, limited reaction volume, and smaller particle will form. If the droplets are larger, so large nanoreactors, potentially larger particles. So, like this, based on the size of nanoreactors, we can control the particle size. So, droplet size is an important parameter which will control the nanoparticle size. So, so one of the most important application of this mini emulsion is nanoparticle polymerization. So we can using this process we can create the organic nanoparticles, magnetic nanoparticles. So so what is the advantages of this process? We can get the good size control, high stability, and scalable also. But what are the limitations? So limitations is since we are adding some surfactant, so it the final nanoparticles can have some may retain surfactant on their surface. So so additional additives are required for additional processing so that purification, so it can the impurities can come. Also droplet stability. So if the system is poorly optimized, it can suffer from aggregation. So this is this was a bottom up method in which we were dispersing one liquid as very small droplet in another immiscible liquid. So this was the bottom up process. Then the next is solid sets. Okay, so apart from physical and chemical methods, there are also biological methods, like in which some bacteria, fungi, algae, enzyme mediated. These are all biological processes which we are using for the synthesis uh, process of nanoparticles. So, like these are also a bottom up approach, and like basically leaving bacteria, and it is a part of green synthesis where microorganisms like bacteria, fungi, algae, these are acting as a biological factories for converting metals and to or other precursors into nanoparticles. So simply it is like some metals and metal ions are there, bacterial biomolecules, it will reduce. So reduction, then nucleation, and nanoparticles are formed. So basic idea is like some bacteria have the ability to interact with metal ions present in their environment. Suppose we introduce silver ions. So bacterial cells contain biomolecules such as proteins, enzymes, amino acids. So some of these biomolecules can act as a reducing agent, and silver plus electron, it will give the neutral atom. So the newly formed atoms, it can form the clusters and the nuclei, and then it will give the Ag. nanoparticles. So like in biological processes also there are, like we can go in detail also, like intracellular synthesis where the nanoparticles will form inside the bacterial cells. Next is extracellular synthesis where the nanoparticles are formed outside the bacterial cells. And so bacteria basically it can act as a reducing agents, it can act as a nucleation sites, capping agents. And so using this process, like we are using biological processes also, nanoparticles are being formed. Then comes the electrochemical process, which is a hybrid process for synthesis of the nanoparticles. So what is happening in the case of electrochemical process? So in the electro, because why it is hybrid, it combines the electrical energy with the chemical reactions. So the basic principle is electrical energy, and then electrochemical reaction will happen, then nucleation and nanomaterial. So it is similar, like electrochemical system consists of anode, cathode, electrolyte and power supply. So nanoparticles will form, suppose if we have a metal ions in solution, when voltage is applied, individual metal is produced near the electrode, and as the concentration will increase they begin to form clusters. I'm not cluster. And once the cluster will become stable, nucleation will happen. So like this it will happen. Similarly CVD is also a hybrid process, and particle arresting in a matrix. So for this process, so this is also a hybrid process, and which is a top down approach for producing the nanoparticles, in which what we are doing here, here it is now. So we have matrix where we will have the dispersed particles, then these particles will confine into this matrix, this particle confinement, and then by help, like with the using the particle confinement process we can get the nanocomposite. So arresting here, it means that the matrix will restrict the motion or movement of the particles, preventing them from coming together, and it will form a larger particle. Suppose like we have atoms, it will form small clusters and it will give us the nanoparticle. So what is the matrix? So what is mean by matrix here? So matrix, Matrix, it is a it is a continuous material surrounding the nanoparticles. So matrix can be a polymer, ceramic, glass, carbon, semiconductor. So the nanoparticles will form the dispersed phase while the matrix form the continuous phase. So like if we imagine nanoparticles are forming inside a material, precursor will give us the atoms and it will give us the nuclei. Then when the nuclei will start growing, it will give us the nanoparticles. So matrix just prevents from agglomeration, limits the particle growth, stabilize the nanoparticles, provides the mechanical support, and mm, so this is an like also when we want to prevent, like for the stability purposes, the matrix method is very helpful. So this is one of the hybrid method for synthesis of nanomaterials. The next is microemulsion geolite. So this is the last hybrid method in such case. So this is a bottom up technique. So in this, what is happening, the key idea is to use we are using the extremely small thermodynamically stable droplets as the confined reaction environment where the geolites precursors will undergo the nucleation. So we have studied what is the microemulsion and what are geolites. So geolites are crystalline porous aluminum silicate materials. So the framework is SiO4 and AlO4. So these form the tetrahedral units. So SiOAN. So when we want geolite nanoparticles, controlling nucleation and crystal growth is very important. So microemulsion provides a confined environment that can restrict the crystal growth. So like typical microemulsion, we can use the oil phase, water phase, surfactant, and geolite precursors. In geolite precursor, we can use the silicon source, aluminum source. So these water droplets, similar in case of mini emulsion, tiny water droplets will form. It will act as a mini nano reactors, and inside the droplets, the precursor species will undergo the hydrolysis and condensation. Then the nucleation will start, and the surfactant will stabilize the interaction between oil and water. And using this approach, we can control the dimensions of the formed nanoparticle. And geolite nanoparticles have a high surface to volume ratio, so it is beneficial for applications such as catalysis and sensing and ion exchange. So, so this was the one method, hybrid method for the synthesis of nanoparticles. Moving further, okay. So if we talk about the thermodynamics of nucleation, so nucleation, what is nucleation? Is the it is a formation of a stable, critical size cluster of a new phase from a parent phase, overcoming an energy barrier, which is in terms of we are saying that gives free energy to the trigger crystallization. So there are two competing energy terms governs the radius r. So this is the formula and this is the plot. So the nanomaterial synthesis, nucleation is the process by which the atoms, ions or molecules in a precursor phase will come together to form a stable nucleus which can subsequently grow into the nanoparticle or crystal. So there is a competition between surface energy and the volume free energy. So we can say that nucleation competition between surface energy and volume. So like imagine we have a super saturated solution containing atoms and molecules of the material we want to synthesize. So now initially they are randomly distributed like atoms in a solution. Now atoms will come together, then there will be a formation of small cluster, not necessarily that it is stable. So it can also break and dissolution. And if it is sufficiently large, so large enough cluster can give to a stable nuclei. So there are two competing contribution to the Gibbs free energy. One is from surface energy. So when the new particles will form, it will create a new interface between the particle and its surrounding. So this interface delta G is greater than 0. Surface because it require energy. So for a spherical nucleus, A is equals to pi r square. So therefore delta G surface will give you 4 pi r square gamma. So where gamma is surface and gamma is the surface energy or interface energy per unit area. So surface energy is proportional to r square. Now at the same time forming the new stable phase can lower the bulk Gibbs free energy. So for a super saturated system, delta G volume is lesser than 0. So for a spherical nucleus, the volume is 4 by 3 pi r cube delta GV. So it is proportional to minus r cube. Now total Gibbs free energy is given by this. So delta GV is lesser than 0. We can write minus. We can write minus also, or we directly know. So for a very small cluster, so for a very small, when the R is here, for a very small cluster, R square surface energy will dominate. Then as the cluster grows, the negative volume contribution becomes increasingly important. So the total free energy reaches a maximum, very delta G star, and this is the nucleation energy barrier. So beyond a certain radius that we call a critical radius, it corresponds to the maximum. That radius correspond to the maximum Gibbs free energy, which will give us the uh, critical radius. So there is also one question on this on the concept of the critical radius, that the critical radius, it is the minimum size a nucleus or atom or cluster of atoms must reach during a phase transformation. Here it is thermodynamically stable and will continue to grow spontaneously. So the nuclei with radius smaller than r will shrink while one larger than r will grow. So higher in surface energy or lower undercooling, it will increase the critical radius, making nucleation more difficult. So So there are homogeneous nucleation versus heterogeneous nucleation and undercooling. So for the case of homogeneous nucleation, nucleation will occur uniformly within the bulk parent phase itself, driven only by the constituent atoms, molecules coming together, and it requires large undercooling since no surface assists the process. In case of heterogeneous, the nucleation barrier is smaller and it happens more easily and at lower undercooling. So, what is undercooling? Cooling a liquid below its equilibrium melting point without solidifying. So, a faster cooling rate than equilibrium requires. So, more undercooling, smaller Δh needed, smaller critical radius, and easier nucleation. Uh, so, the next is this is the growth routes, the llama diagram. So, there are you can see that A, B, and C. So, what is A, B, and C? In the figure A, you can see that the fast nucleation takes place as the solute concentration approaches the supersaturation. So the growth route depicted by curve A is a classical route. So concentration rises to a supersaturation. Spike triggers fast homogeneous nucleation and then it drops by sharply as monomer is consumed by growth, yields narrow monodisperse size distribution. Since the groove depicted by is suggested by Lamer, hence it is called as a Lamer diagram. The second is the curve B. The curve B is like where particles grow through aggregation and resulting in a broader size distribution than the curve A. And the third is Ostwald Rippling. This is what we saw, Ostwald Rippling. So in this case, it favors the growth of the larger particles at the expense of lower ones. So how can we define the Ostwald Rippling process? It is the process by which larger particles grow at the expense of smaller ones in a dispersed system due to due to the difference in the chemical potential between the particles of different radii. So it occurs because smaller particles, if we have small particles, it will have the higher curvature. Also, surface energy will be higher for smaller particle. Then smaller particles will become more soluble in the surrounding medium than the larger particles, and it will lead to the dissolution of the smaller particles and redeposition of their materials on the larger ones. So this process is called, so in this process the nucleation will persist for a longer time, which will allow the both smaller and larger nuclei to coexist. So as the solute concentration will decrease, the larger particles will grow at the expense of smaller ones, and the driving force for this is the reduction in. So what is the driving force for this? The driving force is reduction in total surface energy. So the solute concentration and temperature of the solution will significantly influence the growth dynamics, and crystalline structure, presence of defects also critically affect the final morphology and the size of the particles. So the next is There are some top down routes which are mechanical and lithographic. So we have already studied about ball milling. There is one other, cutting, etching and grinding. So we use, while fabricating the structures, we use the etching methods, grinding and cutting. Using this process, we are doing the converting the bulk material to the nano size features. Then photolithography. So in lithography techniques, there are two options, either optically and the other one is e-beam lithography. So in case of photolithography, we will shine the UV light through a patterned mask. Suppose we want this type of structure. So we will create this mask in which there are holes, so that the light, when we are exposing the light will expose on the certain part, on this part only, and it will generate this, it will transfer the same patterns which we want. Similarly, in case of electron beam lithography, in this case we are using the optical light, but in this case we are using the focused e-beam, which will directly write the pattern, and it uses a soft mask. Like, we don't need a hard mask, we generate the soft mask, and we can achieve the size up to 10 nanometer resolution. Then we have talked about the sputter, in which we were using the argon ion bombardment, and it was creating a plasma. Then it was striking the atom. It was a physical technique, so it was striking the target, and the metal was evaporating and then transporting to the substrate, and then the thin films are formed. So in case of sputter, there are four options: DC sputter, RF sputter, magnetron sputter, and ECR plasma deposition. So in case of DC sputtering, there is high negative voltage on cathode target. Argon plasma will low discharge sputters conductive targets. So, but we can't since like in for we can't use DC sputtering for the insulators because it cannot sustain a discharge. That's why we use the RF sputtering. So for RF sputtering, general frequency is 13.56 megahertz. Alternating voltage continuously, it will flip the electrode polarity so that it will avoid the charge build-up, and it will enable the deposition of the dielectric and insulating films. So like SiO2, ITO, TiO2. So we use the RF sputtering for depositing these. Now, in case of magnetrons sputtering, we can boost the deposition rate because the magnetic field will trap the electrons in a helical path near the target, and it will boost the ionization, hence it will enhance the deposition rate. In case of ECR plasma deposition, 2.45 gigahertz microwaves are using it is resonating with the electron cyclotron motion, and it will increase the higher magnitude. It will increase the 2-3 orders of the magnitude higher ionization density and used for deposition of SiO2, silicon nitride and gallium nitride films. So we have already discussed about CVD and electric arc deposition. Next is ion beam techniques and molecule MBE. So in ion implantation, we are using the ion guns towards a heated substrate. Depending upon energy, it will do, it will form an elemental compound and alloy nanoparticles. We will do the post annealing and improve the crystallinity. And in MBE, we are using a ultra high vacuum, and it gives a very low deposition rates, but the crystallinity, like if we want purity, then we always use MBE. It enables the formation of quantum dots, quantum wells, quantum wires, and the monitoring is in situ, so while depositing also. So when we are doing sputtering, when we are doing the CVD, these are not in situ measurement, but in case of MBE, we can, using the reflected high energy electron diffraction process, we can track the crystallinity and the growth quality in real time. So this is called the in situ process. So this is the table which is saying us the advantages, disadvantages of the top down and bottom up. So advantages are, it is a top down or well established and industry compatible and scalable, and we can, using the lithography technique, we can produce the pattern, desired patterns also. Bottom up, it requires the atomic level precision, defects are fewer, economical raw material use, and tunable surface chemistry. In case of surface quality, or disadvantages are defects, but here the defects are lesser. Surface, in case of surface quality, often rough, it is smooth. So these are the various things, the techniques have we have already seen. Then, uh, so colloidal stability and the DLBO, colloidal stability and the DLBO theory. So what are, like we have already studied that the colloids are the two more phase system where at least one phase has a dimension under a micrometer. Nanometer are a colloid subclass confined to the nanometer range, and dispersed particle will undergo Brownian motion, and it will stable the dispersion versus. So what is the DLO theory? It is a theory used to explain the stability and or aggregation of the colloid and nanoparticles in a liquid. So it is so once the nanoparticles are formed, uh, we want to prevent them from sticking together and forming larger aggregates. So what does it mean by DLVO? So it comes from the scientist. So D stands for Derjaguin, L stands for Landau, V stands for Verwey, and O stands for Overbeek. So these four scientists, from these four scientists, the name this theory DLVO came. So it deals with the van der Waals attraction. So it is from the Leonard John form, which is proportional to 1 by R6. Electron double layer repulsion, where the charged colloidal surfaces attract oppositely charged counterions. It will forming a diffuse Helmholtz double layer, and it will act as like a parallel plate capacitor. So higher electrolyte concentration will compress this layer, and it will weaken the repulsion. So that will promote the aggregation. Then steric hindrance. So absorbed polymers or organic layers physically keep particles apart, like these are acting as a capping agents. So it will increase the particle size and will suppress the van der Waals attraction. So this is the basis of most modern nanoparticle capping strategies. So the net interaction del G is equals to del G attractive plus repulsive, then electrostatic, steric, and the other term. So if the repulsive term will dominate, the colloid will stable. Otherwise, it will repel, and coagulation or network formation will occur. So van der Waals, two nanoparticles experience an attractive interaction when they come sufficiently close. So, and the surrounding liquid response for the electrostatic double layer, the surrounding liquid responsible to its surface charge, and electrostatic. Okay. So these are the four family, like physical, chemical, biological. So the next coming up to the assignment. So since we have already covered all the things, there is not much difficulty in solving the assignment. So which of the following is a top-down approach for nanomaterial synthesis? So this is a bottom-up. Sorry. This is a bottom-up. This is also a bottom-up. In case of ball milling, only we were doing the top-down approach, where we were crushing the larger particles into the smaller one, nanoparticles. Top bottom. So the correct answer is C. The second is, which of the following is the bottom up method? So soldier processes. Etching, grinding, and laser cutting is a top down. and the social method is the bottom up method. So the correct answer is, you can see. Then the term critical radius in nucleation theory represent. So what we say, that critical radius is where the del G is maximum. So it means the nuclei is stable. So the option B is correct. Minimum size of a nucleus must reach to be stable. Then DLBO theory describe interaction colloids. So we saw that DLBO theory were dealing with the van der Waals forces and the electrostatic forces. So the correct answer is C. The next is, which technique can be utilized for synthesis of carbon nanotubes and fullerenes? So we saw that using the electric arc discharge method, we can synthesize the carbon nanotubes and fullerenes. So the answer is C. In RF sputtering, the standard frequencies, we just saw that it is 13.56 megahertz. So the correct answer is B. In sol-gel synthesis, a sol is defined as colloidal suspension of solids in a liquid. So the correct answer is C. Oh, we have studied all. Which synthesis methods allow deposition of monolayers on a substrate? So you can see that ball milling was a ball milling, melt mixing, and microemulsion. These were not. mm, these are not allowing the deposition of monolayers. Only the evaporation, where the target material is evaporating and condensing to the substrate. At their so it was, the correct answer is evaporation. Using evaporation, we can deposit the monolayers. The next is sputter deposition typically involves, we saw that bombardment with ions. So we are using the argon ions. So the correct answer is C. The next is, in hydrothermal synthesis, reactions were carried out under high temperature and pressure in aqueous medium. Which techniques provides atomic level layer control during synthesis? We just saw that using molecular beam epitaxy we can control the atomic level layer deposition. So the correct answer is B. CVD typically involves a reaction of gases on a heated substrate. So it's a chemical, so obviously there will be a chemical reaction will happen and it will deposit on a substrate. So hmm, the correct answer is B. Which force is not involved in the colloidal interaction in according to DLBO theory? So we saw that in DLBO theory there was electric double layer repulsion, steric hindrance, van der Waals attraction, only gravitational pull was not considered. So the correct answer is D. Which one of the following enhances the colloidal stability? So for enhancing the colloidal stability, the steric repulsion is needed. So the correct answer is C. The particle size will not enhance the colloidal stability. Electrostatic repulsion also, high van der Waals attraction will also not enhance. So the correct answer is steric repulsion. Oswald ripening causes reduction in nucleation. We just saw that. What does this mean? It was growth of the larger particles at the expense of smaller ones. The correct answer is B. So what are the this was all about the assignment, and what is the key reminder, what is the key takeaways from this lecture? We saw that the nanomaterial synthesis using this physical, chemical, biological, and hybrid ones methods. Two approaches for synthesis of nanoparticles. One is the top down, where from bulks we were converting into segments and then nanostructure. The other one is bottom up, where the atoms are forming clusters and then providing the nanostructures. Then we talk about nucleation, which is a thermodynamic competition between the volume free energy and the surface energy. We talk about the one critical radius, where nuclei will grow spontaneously. Then we saw the various techniques like CVD, PVD, MBE, and lithography techniques, DLVO theory, so which will tell us the stabilization of the nanoparticles. So this was all about today's lecture. If there is no doubt, then we can hang up the call. Okay, thank you. Okay.